This is the video for Part 2 of Section 4.1, Polynomial Arithmetic and the Division Algorithm. In this video, we want to discuss the division algorithm in polynomial rings. In the case that f is a field, the polynomial ring f bracket x satisfies a division algorithm similar to that for the integers. So this is theorem 4.6. Suppose f is a field. For all f of x, g of x in f bracket x with g of x not equal to 0, there exist unique polynomials q of x and r of x such that f of x equals g of x times q of x plus r of x, and either r of x is equal to 0 or degree of r of x is less than the degree of g of x. So f of x is our dividend polynomial, g of x is our divisor, so we're dividing g of x into f of x, and we obtain a quotient q of x and a remainder r of x, satisfying the equality, and the remainder satisfies the conditions either r of x is equal to 0 or it has degree less than the degree of our divisor g of x. Now if you compare this with the division algorithm for integers, you'll see that it has a very similar structure. The division algorithm for integers says for all integers a and b with b not equal to 0, there exists unique integers q and r such that a is equal to b times q plus r, and the remainder r is greater than or equal to 0 and strictly less than the divisor b. So you see that the equality here has the same structure as the equality for the division algorithm for integers. The remainder satisfies a slightly more complicated condition, however. Since we're dealing with polynomials, we have to account for the possibility that the remainder polynomial is 0. And then our condition, instead of saying the remainder is strictly less than the divisor, we have the condition that the degree of the remainder is strictly less than the degree of the divisor. So before proving the theorem, we first illustrate it with two examples. So for the first example, we want to divide the polynomial f of x equal 3x to the 5th plus 2x to the 4th plus 6x cubed plus 4x squared plus x minus 2 by the polynomial g of x equal 2x cubed plus 1 in q bracket x. So our field is the field q of rational numbers, and f of x is our dividend polynomial, and g of x is our divisor polynomial. So we're dividing g of x into f of x. And so we can start by writing out our notation for dividing one polynomial into another. So this is the standard notation for long division. And we'll start by dividing the leading term 2x cubed of the divisor g of x into the leading term 3x to the 5th of the dividend f of x. So we just look at the leading terms of each of the two polynomials. So this will be 3x to the 5th divided by 2x cubed. And we can write this in an alternative notation. This is going to be 3 times the multiplicative inverse of 2, or 2 to the negative 1. And then our powers of x the resulting power of x when we divide will be x to the 5 minus 3. Okay, so this notation will be important when we look at fields other than the rationals or reals, and so we'll see why we want to use this notation in our next example. So 3 times 2 to the negative 1 is obviously just 3 halves, and then x to the 5 minus 3 is x squared. So this gives the first quotient term, and so we'll put it into our notation. We have 3 halves x squared above the horizontal bar above our dividend. And then for the next step, we're going to multiply the quotient term times the divisor. So we're going to multiply the 3 halves x squared times 2x cubed plus 1. And this will result in the polynomial 3x to the 5th plus 3 halves x squared. Next, we subtract this product from the dividend. So subtract this from f of x, and we obtain the polynomial shown. Now, for our next step, we divide the leading term 2x cubed of the divisor g of x into the leading term 2x to the 4th of the difference. And this will be 2x to the 4th divided by 2x cubed, which is 2 times 2 to the negative 1, x to the 4 minus 3 power, which is just equal to 1x. And this gives our second quotient term, so we'll add it to our quotient. and then multiply the quotient term times the divisor. So we're going to multiply 1x times our divisor, 2x cubed plus 1, and this will give us 2x to the 4th plus x. Then we subtract this product, and we have 6x cubed plus 5/2 x squared minus 2. And then our third step, we're going to divide the leading term 2x cubed of the divisor into the leading term 6x cubed of our difference polynomial. And this will be 6x cubed over 2x cubed, which is 6 times 2 to the negative 1, x to the 3 minus 3 power. And this is just going to be equal to 3. 3 times x to the 0, which is just 1. And so we'll add this into our quotient, and then multiply the quotient term times the divisor. So 3 times 2x cubed plus 1, that will be 6x cubed plus 3, and then subtract this product, and we're left with 5/2 x squared minus 5. Now at this point, the leading term of the divisor g of x has a higher power or degree than the leading term of the difference, so we stop. We can then read off the quotient and remainder. So our quotient is 3/2 x squared plus 1x plus 3, and our remainder is 5/2 x squared minus 5. Okay, for a second example, we're going to divide the polynomial f of x is 3x to the 5th plus 2x to the 4th plus x cubed plus 4x squared plus x plus 3 by g of x is 2x cubed plus 1 again, but this time we're going to do it in z sub 5 bracket x. So our field is z sub 5. And so we'll start the same way. We'll set up our notation for our divisor and dividend. And we're going to start the same way again. Divide the leading term 2x cubed of the divisor g of x into the leading term 3x to the 5th of the dividend f of x. Okay, now when I say divide, what we're really going to be doing is we're going to be taking the coefficient of the dividend, 3, and we're going to be multiplying it times the multiplicative inverse of 2 of our coefficient of the divisor, and then we're going to subtract the powers of the powers of x. So we're going to end up with 3 times 2 to the negative 1, x to the 5 minus 3. And now in z sub 5, the multiplicative inverse of 2 is equal to 3, because 2 times 3 is 6, which is equal to 1 in mod 5. So this is going to be 3 times 3 times x squared. And then 3 times 3 is 9, but in z sub 5, 9 is equal to 4. So this will be 4x squared. And so this is our first quotient term. So we'll put it up above our dividend. Then we're going to multiply the quotient term times the divisor. So we've got 4 times 4x squared times 2x cubed. That will be 8x to the 5th. But in z sub 5, 8 is equal to 3. Plus 4x squared. Then we subtract this product from the dividend. And so we pull down the 2x to the 4th, the 1x cubed, the 4x squareds cancel, pull down the x plus 3. For our second step, we divide the leading term 2x cubed of the divisor into the leading term 2x to the 4th of the difference. And this one is easy, but this is 2 times 2 to the negative 1, x to the 4 minus 3 power. And this will just be 1x. And this gives the second quotient term, and we can add it into our quotient. Now multiply the quotient term times the divisor, so that will just be 2x to the 4th plus x. And then subtract this product, and we're left with 1x cubed plus 3. Okay, one more step. We're going to divide the leading term 2x cubed of the divisor g of x into the leading term 1x cubed of the difference. So this will be 1 times 2 to the negative 1, x to the 3 minus 3 power. And again, 2 to the negative 1, the multiplicative inverse of 2 is 3. So this will be 1 times 3, x to the 0, which is just 1. And this is equal to 3. So that gives us our third quotient term. So we can add it into the quotient and then multiply it times our divisor. So that will be 6x cubed, which is 1x cubed in z5, plus 3. Then we can subtract, and we obtain 0. Okay, now at this point the remainder is 0, so we stop. And we can then read off the quotient and remainder. So the quotient is 4x squared plus x plus 3, and our remainder is 0. We're now ready to prove the theorem. So let's restate it again. So pose f as a field for all f of x g of x in f bracket x with g of x not equal to 0. There exist unique polynomials q of x and r of x such that f of x is equal to g of x, q of x plus r of x, and either r of x is 0 or the degree of r of x is strictly less than the degree of g of x. So we'll start by supposing f of x and g of x in f equal to 0. We then need to show that there exists unique polynomials q of x and r of x satisfying the conditions in the theorem. So we'll first prove existence. And we're going to consider two cases. So case 1, suppose f of x is either 0 or the degree of f of x is strictly less than the degree of g of x. In this case, we're going to choose the quotient q of x equal to 0 and the remainder r of x is equal to f of x. So for both of these possibilities, we'll choose q of x and r of x as shown. Then g of x times q of x plus r of x will be equal to g of x times 0 plus f of x, which is equal to f of x. So the equality holds. Also, either r of x is equal to f of x is equal to 0 in the first instance, or the degree of r of x is equal to the degree of f of x, which is strictly less than the degree of g of x, in the second instance, so the remainder satisfies the required condition. And so this proves existence in case 1. For case 2, we're going to suppose that neither of the possibilities from case 1 hold, so we're going to suppose that f of x is not equal to 0, and the degree of f of x is greater than or equal to the degree of g of x. For instance, using strong induction on n, which is equal to the degree of f of x. So for an induction proof, we'll set it up our usual way. So we need to prove n for all n greater than or equal to 0, p of n, where p of n is the propositional function shown. So p of n is for all f of x, g of x, and f bracket x with g of x not equal to 0 and the degree of f of x equals n. There exists q of x, r of x, and f bracket x such that the equality holds and either r of x is 0 or the degree of r of x is strictly less than the degree of g of x. So we set this up the way we set up our any induction proof. One slight difference here is we're starting our induction at n equals 0 as opposed to starting it at n equal 1, which is more typical. And this is just to allow for the possibility that the degree of our polynomial f of x is equal to 0. So for our basis step, we need to show p of 0. So p of 0 is obtained by substituting n equals 0 in p of n. And so we have our degree of f of x is equal to 0. So to prove p of 0, we'll suppose f of x and g of x and f bracket x are arbitrary, with g of x not equal to 0, and the degree of f of x is equal to 0. Since in this case, the degree of, this is case 2 now, since in case 2, the degree of f of x is greater than or equal to the degree of g of x, then the degree of g of x is equal to 0 also. It follows that both f of x and g of x are constant polynomials since they both have degree 0. So f of x is equal to a and g of x is equal to b for some non-zero elements a and b and f. Since f is a field, then b has a multiplicative inverse, b to the negative 1 in f. So we're going to choose our quotient q of x to be ab inverse and the remainder r of x to be 0. Then f of x is equal to a is equal to b times ab inverse plus 0, which is equal to g of x times q of x plus r of x. So that tells us our equality holds, and r of x is equal to 0 since we chose it to be 0. So the remainder satisfies the required condition. And so this proves p of 0, so the basis step holds. Next, for our induction step, we need to show for all n greater than or equal to 1, p of 0 and p of 1 all the way down to p of n minus 1 implies p of n. Okay, since we're using strong induction, our induction hypothesis is not only that p of n minus 1 holds, but p of 0, p of 1, all the way up to p of n minus 1 hold. So let's suppose n is an arbitrary positive integer, and we'll suppose our hypothesis is holds, so p of 0 and p of 1 all the way down to p of n minus 1 are true. We then need to show p of n. So to show p of n, we're going to suppose f of x and g of x and f bracket x are arbitrary, with g of x not equal to 0 and the degree of f of x is equal to n. And let's go ahead and write out what f of x and g of x are. So we'll suppose that f of x is the polynomial a sub n x to the n plus dot 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 down to a sub 2x squared plus a1x plus a0. And g of x is the polynomial b sub m x to the m down to b sub 2 x squared plus b1x plus b0. With a sub n and b sub m both not equal to 0. So our divisor g of x is always assumed to be non-zero, and our polynomial f of x in case 2 was supposed to be non-zero as well. So both f of x and g of x are non-zero polynomials, and so we're just now, since the degree of g of x is less than or equal to the degree of f of x, then m is less than or equal to n. So we're going to start by dividing g of x into f of x following the same procedure we used in the two long division examples. So I'll go ahead and I'll set up a long division notation with g of x is the polynomial b sub m x to the m plus dot 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 down to b sub 0. And then our dividend polynomial f of x is our long division. Well, let me back up just a little bit. Now, since f is a field and b sub m is not equal to 0, then b sub m has a multiplicative inverse. And so we start our long division by dividing the leading term b sub m x to the m of the divisor g of x into the leading term a sub n x to the n of the dividend f of x. And so this gives the quotient term a sub n b sub m to the negative 1 x to the n minus m. So we'll put our first quotient term up there. Then we multiply this quotient term times the divisor to obtain, well, this is a sub n b sub m to the negative 1 x to the n minus m times g of x. And substituting what g of x is, then this is equal to a sub n x to the n plus a bunch of other terms that we're not particularly interested in. But we're only interested in the first term, and in the first term, the b sub m to the negative 1 times b sub m cancel one another, and then x to the n minus m times x to the m results in x to the n. So our first term is the same as the first term in f of x. It's a sub n x to the n. Then when we subtract this product from f of x, since the product and f of x have the same leading term, then this difference has degree less than n, or is possibly the 0 polynomial. So the first terms cancel one another after we subtract, and we're left either with a polynomial with degree strictly less than n, or possibly the 0 polynomial if all the terms cancel. Now in the case that this difference has degree less than n, then the induction hypothesis implies there exist quotient and remainder polynomials. In the case that this difference is the 0 polynomial, then it follows from case 1 that there exist quotient and remainder polynomials. Okay, back in case 1, one of the possibilities was that our dividend polynomial f of x was 0. And so we showed in that case that there exist quotient and remainder polynomials satisfying the required conditions. So in either case, we obtain a quotient and remainder polynomials either from the induction hypothesis or from case 1. So there exist polynomials q1 of x and r1 of x such that this difference polynomial f of x minus a sub n b sub m to the negative 1 x to the n minus m times g of x is equal to g of x times q1 of x plus r1 of x, and either r1 of x is 0 or the degree of r1 of x is strictly less than the degree of g of x. So now solving our equality there for f of x, we obtain f of x is a sub n b sub m to the negative 1 x to the n minus m times g of x plus g of x q1 of x plus r1 of x. And the first two terms on the right-hand side have a common factor g of x. So we can rewrite this as g of x times a sub n b sub m to the negative 1 x to the n minus m plus q1 of x, plus our remainder r1 of x is just sitting there by itself. And then we can choose q of x to be that polynomial in the brackets, so a sub n b sub m to the negative 1 x to the n minus m plus q1 of x, and we'll choose r of x just to be r1 of x, no change there for the remainder. So then f of x is equal to g of x times q of x plus r of x, and the remainder is either 0 or has degree strictly less than the degree of g of x. So this proves p of n. We've proved existence of our quotient and remainder satisfying the required conditions. And so this proves p of n, which proves the induction step. And thus, for all n greater than or equal to 0, p of n is true by the principle of complete induction. And this completes the existence part of the proof. Next, we need to show that the quotient q of x and remainder r of x are unique. So let's suppose q2 of x and r2 of x are polynomials that also satisfy the conditions of the quotient and remainder, namely that f of x is equal to g of x times q2 of x plus r2 of x, and either r2 of x is 0 or the degree of r2 of x is less than the degree of g of x. We then need to show that q2 of x is equal to q of x and r2 of x is equal to r of x. So this is a standard uniqueness proof. We suppose we have two things and we show that they're actually equal to one another. Now, since f of x is equal to g of x q of x plus r of x, and f of x is g of x q2 of x plus r2 of x, then we can set these two expressions equal to one another. And then we can take the g of x terms all to the left side and the remainder terms all to the right side. And so this implies g of x times the quantity q of x minus q2 of x is equal to r2 of x minus r of x. Now it follows from looking at this equality that q2 of x is equal to q of x if and only if r2 of x is equal to r of x. So the left side is 0 if and only if q of x minus q2 of x is 0, which holds if and only if the right side is 0. So it suffices to prove q2 of x is equal to r of x. And we'll use a proof by contradiction to show this. So let's suppose that q2 of x is not equal to q of x. Then q of x minus q2 of x is not equal to 0, and r2 of x minus r of x is not equal to 0. And by theorem 4.2, the degree of g of x times the quantity q of x minus q2 of x will be equal to the degree of g of x plus the degree of q of x minus q2 of x, which implies that the degree of g of x times q of x minus q2 of x is greater than or equal to the degree of g of x. However, since both r of x and r2 of x are either 0 or have degree less than the degree of g of x, then the degree of the difference r2 of x minus r of x will be strictly less than the degree of g of x. But g of x times q of x minus q2 of x is equal to r2 of x minus r of x. So we've shown that the left side of this equation has degree greater than or equal to the degree of g of x, but the right side has degree strictly less than the degree of g of x. So these inequalities imply a contradiction. So therefore q2 of x is equal to q of x, and r2 of x is equal to r of x as required, so q of x and r of x are unique. And so this completes the proof of the theorem.